Hello everyone. Welcome to the topic of mathematical system. What are the two important questions in the study of mathematics? When is a mathematical argument correct? What method can be used to construct mathematical arguments? A mathematical system consists of undefined terms, definitions, and axioms. Undefined terms are the basic building blocks of a mathematical system. These are words that are accepted as starting concepts of a mathematical system. For example, in geometry, undefined terms in geometry are point and line. A definition is a proposition constructed from undefined terms and previously accepted concepts in order to create a new concept. For example, in geometry, example definitions are such as two triangles are congruent if their vertices can be paired, so that the corresponding sides are equal, and so are the corresponding angles. So, the two triangles in the diagram are congruent. Two angles are supplementary if the sum of their measures is 180 degrees, so angles in A and B in the diagram are supplementary. An axiom is a proposition accepted as true, without proof, within the mathematical system. For example, in geometry, example axioms are such as given two distinct points, there is exactly one line that contains them. Given a line, and a point not on the line, there is exactly one line through the point, which is parallel to the line. AB is a line, and C is a point not on the line. A parallel line through point C is drawn as shown in the diagram. A theorem is a proposition in the form of P, then Q, which can be proven to be true by using a sequence of logical steps and, on the basis of established definitions, axioms, and proven theorems. For example, in geometry, example theorem are such as if two sides of a triangle is equal, then the angle opposite them are equal. If the diagonals of a quadrilateral bisect each other, the quadrilateral is a parallelogram. A lemma is a small theorem, which is used to prove a bigger theorem. A corollary is a theorem that can be proven to be a logical consequence of another theorem. A proof is a logical argument that consists of a series of steps, using propositions, to demonstrate a specific statement, proposition, or mathematical formula is true. There are two types of proof: direct proof and indirect proof. Let's learn direct proof in this video.
Today we're starting direct proofs, so I should probably start with some terminology, and I think the oddest thing I'm going to do is give a definition of the word definition, at least how it's used in math. So a definition, I'm going to do very, very short, concise, wordy proofs, or wordy definitions, because I can say the long stuff, but this is just something given. Now, definitions are a little bit interesting because they don't require proofs. So, you never, ever have to prove a definition. So if I say, let M be a matrix 1, 2, 3, 4, then I don't have to prove that M is a matrix because this is my definition statement. A theorem, on the other hand, is something to be proved. And I'm sorry my writing is just a tad messy here. But, so I don't like writing long definitions out while doing videos. I prefer doing them before. But a theorem is something to be proved, and it usually results in these other subproofs called corollaries. And what these are these just happen to be little things that come about because the theorem is true. So if I have a theorem that says all numbers are either odd or even, the corollary is that any number divisible by 3, sorry, that's a really bad example, any number divisible by 2 is going to be even. So that's a little corollary kind of thing. Anyways, terminology is boring, that's not why you're here. Let's get to the direct proof. And I'm using propositional logic because it is a very good way to explain how proofs are done. So, in a direct proof, we have a statement that says, if phi, then psi. And what we do here is we assume phi, and we have to show that psi. So, for instance, if I say, well, let's just jump straight to the actual question I wrote down. If x is odd, then x squared is odd. So, first of all, we're making an if-then statement, so to prove that it's true, well, we say, okay, well, let's just assume x is odd. Now, something about odd numbers is that any odd number can be written in the form 2n plus 1. So now we have to prove that x squared is odd. Okay, well, that shouldn't be too bad. Let's square both sides of this equation. So x squared is going to be the same thing as 2n plus 1 squared, which if we factor this out, it is going to be 4n squared plus 4n plus 1. Okay, so that's not too bad. So what we can see here is that we've actually proven that x squared is also odd. Because we have, well, we know that 2n plus 1 is odd, so we could reduce it to 2n plus 1. I'm not going to go that far, but I am going to say we can factor out a 2 and an n from the first two, so we get 2n plus 2, and then we get 1 out there, which really is, if you see this, this is 2n plus 1, it just happens that the n has to be multiplied by an even number, which is 2n plus 2. So we have actually proven that if x is odd, then x squared is odd. So that is a direct proof. It is a direct proof because we're assuming the antecedent is true. So I will repeat this again. You assume the antecedent is true, and then you prove the conclusion, or the consequent, depending on the vocabulary you wish to use. And that is a direct proof. I'm wondering if I have... oh yes, of course I have one more. There is a little section of direct proofs that I should cover now. I guess it's better to cover it now than later. But if we say if x comma y are odd, then x, y are odd. Well, this isn't exactly crucial for this example, but if we were to say x or y, then we'd have to do a proof by case, which is a little bit different. We have to take different cases where, okay, just x is odd, just y is odd, and then both are odd. We'd have to do that. But luckily for this, we're saying that both are odd. So we're going to let x be equal to 2k plus 1. We're going to let y equal 2j plus 1. So then x times y is going to be 2k plus 1 times 2j plus 1, which then when we factor this out, we're going to get 4kj plus 2k plus 2j plus 1. Okay, so the key thing when you deal with these odd or even proofs is that you have a plus 1 at the end. And if this is the case, then we can say that yes, it is odd. So again, there's another example of a direct proof. If we were to say x or y, we'd have to do a case 1, where x is equal to 2k plus 1, y is equal to 2j. We have to have a case 2 where x is equal to 2k and y is equal to 2j plus 1, and then this would be our case 3 up here, and all of these would have to be correct. Of course, I am trying to think if that is the case, if x or y is odd. Well, it seems like that would not hold then, because if anything times an even number is even, so in this case, case 1 and case 2 would fail, therefore the whole thing would not be true. But that would be a proof by case, which can be a direct proof or an indirect proof, which we'll see in the next video. But I think direct proofs are pretty intuitive. In fact, if you were to do a course without teaching what a proof was, a direct proof would probably be what everyone did. So that shouldn't be that bad. If you have any questions on this, please leave them in the comments. And if not, hopefully you understand this and are doing very, very well.
Let's look at another video. This time is about indirect proof.
Welcome to an introduction to indirect proof. The goals are to define indirect proof and then provide two basic examples of indirect proof. So far our proofs have been direct proofs. The conclusion followed from a series of definitions and previous proven theorems. Indirect proof is a proof when we temporarily assume the conclusion is not true, and then we reach a contradiction to our assumption, therefore proving the conclusion is true. So here are the steps to an indirect proof. Step 1, again, we temporarily assume the conclusion is not true, and then we logically reason until we reach a contradiction, and then we finish by stating that the temporary assumption must be false, therefore the initial conclusion must be true. Let's take a look at a couple basic examples of indirect proof so we get a better feel for this type of proof. We'll first take a look at an indirect algebraic proof. We want to prove that if x equals 5, then 2x plus 4 cannot equal 12. So by following the steps of indirect proof, we'll start by assuming that the opposite is true, meaning if x equals 5, then 2x plus 4 is equal to 12. Now what we'll do is go ahead and solve this equation, and then hopefully reach a contradiction. Let's give it a try. So we're going to solve 2x plus 4 equals 12. So the first step would be to subtract 4 on both sides. So we'd have 2x equals 8. And this would be from the subtraction property of equality. The next step would be to divide both sides by 2. This gives us x equals 4. And this was the division property of equality. And x equals 4 contradicts our assumption that if x equals 5, 2x plus 4 equals 12. And this is the key to an indirect proof. Once we reach the contradiction, we can state that our assumption is false, therefore the original statement must be true. Let's go ahead and write this out. So x equals 4 contradicts that x equals 5. So as a result, our assumption is false. Therefore, 2x plus 4 cannot equal 12. And this is exactly what we were trying to prove from above. If x equals 5, then 2x plus 4 cannot equal 12. Let's take a look at another example. If triangle ABC is isosceles, then the base angles cannot equal 95 degrees. Again, we want to prove this statement by using an indirect proof, so we'll start by assuming the opposite. Well, the opposite would be that the measure of the base angles is 95 degrees. So let's see if we can contradict this statement. Well, if the base angles measure 95 degrees, the sum of the base angles would be 95 degrees plus 95 degrees, which is equal to 190 degrees. Remember, the base angles of an isosceles triangle are the angles that are opposite the congruent sides, those two angles there. By now we should know this is not possible because this contradicts the triangular sum theorem, which states the sum of the interior angles of a triangle is equal to 180 degrees. So if the sum of the interior angles is equal to 180 degrees and the sum of the base angles here is 190, this is all we need to prove the given statement because this is an obvious contradiction. Therefore, we can conclude that the sum of the base angles of an isosceles triangle cannot equal 95 degrees. And we have our indirect proof. So I know these examples are pretty basic, but hopefully it gives you an idea of the format of indirect proof. I hope you found this helpful.